Okay, so any questions? Any questions on the determining whether they're same meso definitions? So we'll just kind of finish up here then where we left off, which was that whenever you have a molecule with two chiral centers, the first thing you're probably going to have to do is you're going to have to check and make sure that doesn't have the possibility of being the same meso compound, because if it's the same meso compound, then you're going to think it's the same, or you might even think it's an enantiomer if you were to do the R and the S configurations, because this is where R and S breaks down. If you had the same meso compound, you might get that one is RR and the other is SS, but if you don't actually check to see if it's meso, you're going to say, oh, those are enantiomers, when in fact they're not. They're the same meso compound. So when you're looking at that in a Fisher projection, you want to make sure that you look at the top three groups, the bottom three groups, and if it's the same three groups on both sides, then you're going to have to check and see, is each molecule meso or not. If you have two Fisher, or if you have two Newman projections, you're going to have to check the front three groups versus the back three groups. And if those are the same front three groups, the same back three groups, it could be meso as well. And so then you'll have to check both of those structures and see whether they're meso or not meso. Okay. So for the ones that I've written here, which are not, I don't think, the same ones that I wrote yesterday, for each one, is it meso or is it not meso? Which one? The first one is not meso. Do we agree with that? That the first one's not meso? Agree? Don't agree? Agree. Everybody agree? So when you have two groups that are lined up, if the other two are, it's meso. If they're not, they're either are or they aren't. So in this case, with them not being lined up, this one is definitely not meso. Now what about the one on the right? Is it meso or not meso? Not meso? Meso?
When you rotate, so for example, if you could rotate the bottom of something, you can only rotate that once, correct?
No, you can rotate as many times as you need to try and line up the groups. So if you wanted to rotate the bottom carbon, are you going to go clockwise or counterclockwise? So you go counterclockwise so that we can bring the OH up here. We could bring the methyl group over here. We could bring the hydrogen there. So do the groups line up? Do they line up to give the mirror plane? And the answer is yes. So if I rotate the bottom carbon or the top carbon, then I can go ahead and line them up, Brandon.
Well, I just have a question because the example we used yesterday, where we had, the same reaction, where you had the hydrogen, you had chloride on the left, methyl group on the right. And then at the bottom, you had a methyl group on the left, chloride on the right, and then hydrogen at the bottom.
Right.
You had it with it.
Right, that one wasn't meso because the hydrogens are already lined up in their position. Remember, for a Fisher projection to be meso, it has to look like this. So we have to line up the two vertical positions, and then we've got to try and line the left and right positions so that we can see the mirror plane that cuts through the center of the molecule. So down here, if you line up the H's, you'll never be able to line up the methyl and the chlorine because the H's are already lined up. And that's the same thing over here. The methyl groups are already lined up, and this hydrogen, there's no mirror plane here. The mirror plane cannot be cut through the molecule. That's a mirror image, but those two aren't. So if we come to the one over here, when I started, the original starting point was not the original starting point here. None of those groups are lined up, so now we've got to try and line them up.
Okay.
So we could say we can line up any two groups we want. So we could say I want to line up the OHs. So if I line up the OHs, I'd say, well, let's bring this OH over here. Let's bring this methyl group over here. Let's bring that H there. So that now the H is here, the OH is here, and the CH3 group is over here, and now they line up to give you the mirror plane. So that's what's making the right-hand molecule meso. So if none of the groups are lined up, you have to rotate the top or the bottom to try and line up two groups. And what will happen is once you line up the two groups, either the other two groups will fall into place to create the mirror plane, then it's meso, or they won't, at which point it's not meso. And the same thing would be true for the Newman projection. We want to line up a Newman projection in an eclipsed conformation so that the groups that are eclipsing are all the same, because then the mirror plane cuts through the center of that bond. So if two groups are already lined up, you either see the meso or you don't see the meso. And if the groups aren't lined up, then you've got to rotate one and the other, and then they'll either line up or they won't. Does that make sense? Oh, Jenny?
So given a staggered Newman projection, you can rotate it so that it is
Right.
the eclipsed version.
Right. You want to rotate this instead of the full 120 degrees. You would just want to rotate these groups 60 to make them eclipsed, sort of just like you did with the just like you do when you write out the 6 different Newman projections. You have to take a staggered one, you have to make it eclipsed, and then you rotate 120 degrees for the rest of them to make the rest of the eclipse. And there's probably different patterns. There's different patterns that if once you do one, you might look at it and you might say, I don't even need to rotate that, I can see it's meso. But my suggestion is take a minute and rotate it. And if you're under pressure, still do it on paper. So for those two molecules then, one's meso and one's not meso. So if you think about the relationship then between those two molecules, if the molecule is meso, right, let's if we look at this one, this generic one, that's meso. What does it mean when it's not meso? It means that I took one of these two chiral centers and I did what to its configuration? I made it the other. What we'll call here in a day or two, inversion of configuration. I inverted it from R to S or S to R. So whenever you have a not meso and a meso combination, those two are automatically going to be diastereomers. So a meso not meso combination is automatically diastereomers. And statistically, that's more likely to happen than them being the same meso compound, or them being enantiomers. If you have one molecule, it has two diastereomers, but only one enantiomer, and only one same. That doesn't mean you're going to play the statistics and guess, but I suppose you could. The only thing that works there is if I'm totally random, which I may or may not be. So you have to kind of look at that. But if you were looking, no. So that's the difference, Ellie.
Could we do an example of a not meso pair, like where we have determined if enantiomers or same?
Like we had yesterday?
Yeah.
Okay, so let's start with the left non-meso pair. So the left non-meso pair had the two methyls. Vertically, it had an H, and an OH, and an OH, and an H. So that's not meso, so let me draw this one so that it's also not meso. Maybe I should probably hide it. So we already know that the left one is not meso if I wrote it exactly the same. And we should double check the right one and make sure it's not meso as well. Because even though my intention was to make it not meso, I may or may not have gotten it. So is the right one not meso? It's not meso because the two methyl groups are lined up and the other two can't. So it's also not meso. So now my choices are, these are either the same or they're enantiomers. And in order to do that, in order to analyze that, now I'm down to my two methods. How many switches would it take me to get, and I'm going to break them up into the two carbons. So for the top carbon, how many switches would it take to get from here to here? Or the other thing I can try and do is line them up so they're in the same orientation, but they'll either be in the same orientation or they'll be mirror images. So you can use either method to do that. So I guess the question is, how many switches does it take? We could do the switches first. How many switches does it take to go from left to right? To turn the left into the right top carbon. Two. So I've got to switch the methyl and the hydrogen in order to line up the hydrogen, and then I've got to switch the OH and the CH3 to now make the left one into the right one. So I did 2 switches on top. And so what does that mean for the top carbon? Is it the same configuration or is it opposite configuration? Same. So the top one is the same. How about the bottom one? Same. We agree it's the same. So again, we can count switches or we can do this. I'm going to line up the methyl group, so I'm going to rotate this methyl group here. That's going to rotate the hydrogen over here. And it's going to rotate the OH down here. When I line those 2 up, do the other groups line up in exactly the same position? Yes. Now, if you line up the 2 groups, it's either one of 2 things going to happen. The other 2 groups are going to line up, or the other 2 groups aren't going to line up. So if they line up, they're the same. If they don't, it's opposite. No.
Why would 2 meso compounds never be bonds?
Because if I switch, let's take this as an example. So if I turn that into its, right now, we just found out that these 2 molecules are what? Top carbon's the same, bottom carbon's the same. That means overall, they are the same, not meso compound. So they're the same compound and they're not meso. Because you could be same and be meso. That's why they're same, not meso, and same meso. So why can 2 not mesos ever be diastereomers? The only way they would be diastereomers is if the top carbon was the same or opposite and the bottom carbon was the opposite pair. Okay? So if we take this not meso compound and we write its diastereomer, that means that the methyl groups are already switched, are already lined up, right? So what do you want to do? Take the top or bottom carbon and make it opposite. Top, okay. So if we want to make the top carbon its opposite configuration, what should I do? I should switch 2 groups and stop. Because now I changed the configuration. And in doing so, now the molecule is meso. So when you have 2 not meso compounds, they can't be diastereomers because the only way they're diastereomers is if one is meso and one is not. Because the not meso compound, when you switch or when you invert one of its chiral centers, becomes meso. Or the meso compound, when you invert one of its chiral centers and only one of it, it becomes not meso. So the meso not meso pair is always going to be diastereomers. And if they're both meso, then they're the same meso compound. And if they're both not meso, like this one, then it could be that they're the same, but they're not meso. Or it could be that they are enantiomers. And so for 2 chiral centers, you always have those 3 possible. If you have 2 chiral centers where the top carbon and the bottom carbon have the same 3 groups attached, it's like we did yesterday. We're down to 3 molecules that are possible. The meso and then the DL pair. Those 2 being enantiomers, but you could have the same or the mirror image of each one of those. So what's my point? I guess my point with these is that when you see that they both have the same groups attached, you could probably save yourself a little bit of work if you just determine whether they're meso or not meso to begin with. Because 2 of the 4 possibilities will be immediately clear. They'll either be not meso, meso, or both meso. If they're both not meso, then you've got to figure out are the enantiomers are the same. So, statistically, 50% of the time you're only going to have to do one step. But with these problems, I may take a few minutes myself and get to the answer I want. So you may see one of these that is meso, not meso, but you may see one that is one of the other 3 combinations. Because I usually tend not to just let myself be random on this. And the same thing would be true for the Newman projections. Front 3 groups, same as the back 3 groups, gotta check that they're both meso or not meso. And for the we didn't do a pair of Newman projections, did we? I don't think. So if you're looking at Newman projections, there probably was a time when I used to suggest to people that if they had a Newman projection, that they might want to put it into a Fisher projection and then make the comparisons, but that doesn't make any sense. So let's say you had these 2 Newman projections. And again, on Monday, you're going to have A, B, C, and D. You're going to have they're either the same but not meso, they're the same meso compound, they're enantiomers, or they're diastereomers. Those are going to be your 4 choices for the final answer. So, what are these 2? Or is there a twist here? What do I have to do first in this molecule? In this problem? Check. Okay, so check whether the front three are the same as the back 3. So are the front 3 the same as the back 3? No. So this can't be meso. They still could be the same. They still could be the same and not meso. They still could be enantiomers or diastereomers. Anybody have an answer that they want to share? No answer to share?
This is where you consider that,
We could. We could. We could. Anybody have an answer? How about this? Front carbon, same or opposite? 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 My issue is I can't tell. I can't tell if the front carbon is the same or the opposite, because in the molecule on the left, the front carbon has the chlorine, and in the molecule on the right, the front carbon has the Br. Did you rotate the molecule around to make that comparison? Just you compared this one to this one. Well, but so the issue is there's a chlorine at the top here, but over here there's a bromine at the top. So I can't compare those directly. So I got to put these two molecules in exactly the same orientation. If yes, if I look at the right one, if I look at the right one and I do a flip in my head, which is always a dangerous thing, I think the carbon with the chlorine, they're opposite configuration. Well, so we got to do something here, because we can't make the comparison directly like we've done in the past. And you might as well see this because they're in some of the practice problems, and they usually filter their way to the exam. So not only do we have to check and make sure that it's not meso, but we also have to make sure that the two molecules are in exactly the same orientation, because if they're not, it was like doing a Fisher projection against a tetrahedron yesterday. We couldn't do that. We had to do RNS. We could do RNS here, but I don't want to do RNS. I just want to look at them. So I've got to take this molecule on the right, and I've got to rotate it 180 degrees and bring the back carbon forward. So when I do that, what's going to happen? When I do that, the front carbon is now going to look like that, because the back carbon, the methyl's down. So when I rotate it around, I'm going to have that down position. So the methyl group that was in the back is now going to come forward. What happens to the chlorine? If I rotate this 180 degrees, the chlorine that is now on the right ends up on the left. So the chlorine's going to be over here, and then the hydrogen's going to be over there. So this is as if I was behind the molecule looking at it forward. And if you can't picture that, then you just need to take the molecule and rotate it 180 degrees, which means the back carbon is going to look like this. So that means the bromine's going to be in the vertical position. The methyl and the hydrogen then go from left to right, they interchange. So now I have this molecule and this molecule in the same orientation, except I really don't yet. But at least I've got the front carbon with the same front carbon and the same back carbon. At least I got that now. Does that make sense? Nobody's head is either on the table or bounced off the table from just going. It's hard to tell glazed over because it's still early. But I want to rotate the molecule so that I'm looking at the same front carbon and the same back carbon. Now the problem is that the front carbon isn't in the same orientation, so let's just do a quick rotation and rotate the chlorine up, the hydrogen down, and the methyl group there, so that now I'm going to convert. So here I did a 180 degree rotation to get the front, to interchange the front to the back and vice versa. So now I'm going to rotate so that the two front carbons have exactly the same orientation. And what do I need to do with the back carbon? How about I just rotate the bromine over here and then bring the methyl group up and bring the hydrogen down, so now it's in the same orientation. So now I could make the comparison. Maybe. So now are we in a position to compare front to front and back to back? Front to front and back to back. So if we wanted to do that, what about the front carbon? Is the front carbon in the same configuration or opposite configuration now? So I'm looking at the front carbon here and the front carbon down here. Same or opposite? Opposite. How'd you know they're opposite? So for this one, the chlorines are already kind of lined up, right? And so are the hydrogens and the methyl group in the same position? No. So one group's lined up, the other two aren't. That makes them opposite. So in this case, the front carbon is opposite in both, is opposite of each other. And then what about the back carbon? Well, the reason I moved the bromine, the reason I rotated the bromine over here was so that I could line up the bromine there. When I lined up the bromine there, what happened? Do the methyl and the hydrogen match up? No? No? So the bromine's lined up, but the methyl and hydrogen don't. So what does that mean? That means it's opposite. So front carbon's opposite, back carbon's opposite. These two are enantiomers. Right? Because every single carbon has the opposite configuration. So that makes these two enantiomers. They're both both carbons are opposite in configuration.
So would you like projections to look both phases of RNS?
Yeah, it's okay. But if you're going to use the method that works best for you. You can use RNS as long as one thing doesn't happen. That it has the possibility of being meso. Because RNS will not work if the compound could be meso.
So if we determine it's not meso.
You can use RNS. You can use RNS. Now you're going to have to turn that Newman projection into like a Fisher or a Sawhorse projection in order to make the RNS determination. Should I show you this? I can show you this. That's what the front carbon looks like. So, could you use the rule of I just have to put the fourth priority group on the dashed line? You can, right? You could, but and this would be perfectly fine, right? So you'd have to say, okay, for this front carbon right here, I've got a chlorine, a methyl, a hydrogen, and something other than a methyl. So what's group number 1? Chlorine. What's group number 2? Sorry. What's group number 4? Hydrogen. So I'm converting this into sort of a tetrahedron. What's the methyl group? The methyl group's automatically number 3 because the group with the bromine is going to be number 2. So if you wanted to look at the front carbon and say, here's my numbers, but it really, well, I guess it kind of looks like this, except it really doesn't. So, and I didn't write it the right way. Let me erase it and put it in. So really, it looks like this. So if you want to, you could say, yeah, I have number 1, number 3, number 2 is in the back, and number 4 is there. And the rule is, I got to put number 4 behind me, so I'll switch 2 and 4, and I'll switch 1 and 3. So now going from 1 to 2 to 3 is S. So actually the front carbon has the S configuration. So if you wanted to, you could do RNS without ever turning it into a Newman projection or a Sawhorse projection. But if you see that and it makes sense, great. If it doesn't, you could play with it, but otherwise, if you want to do RNS, you'd have to do that. And since I went down this rabbit hole, could you do the back carbon without ever rotating it? Yes, but what would the back carbon look like? The back carbon would have 3 dashed positions, and the forward position would be the bold. So you'd have to look at the back carbon, put the numbers in place, and then make it so that the 4 group was on one of the dashed wedges. So for the back carbon here, hydrogen is 4, bromine's 1, methyl still 3, 2. So now going from 1 to 2 to 3 is what? Still counterclockwise. So if you took this molecule and I asked you, hey, for this one, what's the configuration of the front carbon? I get SS, and I think that would be correct. So if that would make sense, you could do it that way and never have to convert the Newman into a Sawhorse or into a Fisher projection. But I don't know. You have to know that that's what you're looking at. Once you can see that. Now, I think I said yesterday, if you could try and take the cyclohexane ring and do this analysis on it, but then you've got to, if you can see it in your head, you're okay. So in other words, what you could do is you could say, okay, here's my cyclohexane. The biggest problem here is that, let's say for instance we take that carbon and I want to put bold and dashed wedges to it while it's in the chair. These two positions would be in the plane. This would be bold. So in other words, here's 1, 2, 3, and 4. 1 and 2 are in the plane, 3's behind, and 4's in front. So if you could see that this carbon actually is in this spatial orientation, you wouldn't even have to take the cyclohexane and make it flat in order to determine RNS. But if you're going to do that, you have to make sure that you see the appropriate orientation of every single carbon of those 6. Whereas if I just take this and I make it flat, I'm working with tetrahedron. So this would have a higher level of difficulty, trying to remember exactly what orientation each of the 6 carbons is. And this isn't diving, so you don't get a degree of difficulty. It's either right or wrong. So you want to use the simplest method you can. But if you can see that, I've had students in the past go, well, isn't this one like this? Yes. So then I choose one of the more obscure ones and I say, what's that one? And then they're like, I don't know. And I said, well, see, that's a difficulty. You got to know all 6. Otherwise, it's just an easy flip to go to here. It's just an easy flip to go to that. But you could do a Newman projection without ever rotating it. So if you want to try that, you can try that with some of the practice problems. But if not, just turn it sideways into a sawhorse. Or, again, there's the videos on how to turn it into a Fisher if you want. So in yesterday's folder, there are problem sets with two molecules asking you what are their relationships. And there's an answer key that goes with that as well. So I'm going to strongly recommend you do as many of those problems as you can. Because for Monday's exam, we're looking at, for the idea of chirality, if I wanted to, the kinds of problems I could ask you, I could give you a molecule and say, circle all of the chiral carbons. Because that's the first thing we started with. And then maybe some definitions, like what's the definition of an enantiomers, what's the definition of diastereomers, what's the definition of a meso compound. And then it's really then down to RNS, determining RNS configurations on any of the orientations of these molecules, Newmans, Fishers, tetrahedra. And then the relationships between the two molecules. They're in yesterday's folder on Canvas. Yeah, I'll send you a list of topics. That's sort of what I'm doing now. So if you're writing it down, then you don't need the list, but I'll send a list. And are there other problems on every one of those? Yes. They're in the Canvas folders. So that's the chirality. And also by basic definitions, I could also ask you, for instance, what physical property is different with enantiomers? Apparently, that's a really good question. The way they interact with plain polarized light, that's the only one that's different. So that's the stereochemistry. So at the beginning of chapter 6, they started with alkenes. And they started with alkenes, bless you. The first thing, if we're using a traditional approach to this, and I guess this is what we call our second functional group. So the way organic chemistry is typically organized in almost all the books, and anytime anybody's tried to write a book differently than this, it's failed, or nobody adopts it, is that there's 11 plus million organic compounds. And if you think organic chemistry sucks now, which is what my doctor told me, well, it sucks to teach organic chemistry. It might suck to take it, but I don't know if it sucks that bad to teach it, although some are. If you had to know the reactivities of every one of those 11 million organic molecules, we would make no progress in organic chemistry. So if we can group the atoms together in what are called functional groups, then we've got somewhere in the neighborhood of about a dozen to 20, if you really want to get specific about different functional groups. Then what happens is, fortunately, whoever designed this said, for functional groups, they react pretty much the same. So I don't have to know the reactivity of all 11 million organics. I just have to know what functional groups do. And then there may be a little bit of tweaking in terms of they might react a little bit differently. But for the most part, that functional group reacts the same. It has very similar physical properties. So now we don't have to worry about, learning every individual molecule. If you have a carbon attached to an OH, that's an alcohol. And for the most part, alcohols have the same physical and chemical properties regardless of the R group that's attached. And that's not totally true, because some alcohols are water soluble and some aren't. And some alcohols are more acidic than others. But for the most part, the alcohol reacts the same whether it's got a methyl, ethyl, propyl, isopropyl, butyl, decyl. They pretty much react the same. So all the organic books, including this one, are organized according to functional groups. And so what we just talked about was alkanes. But to be honest, alkanes are nothing more than the skeletons on which you hang the functional groups off of. So alkanes are very unreactive, but the functional groups aren't. They are reactive. And so when you're doing organic synthesis, when you're converting A to B to C to D to whatever letter of the alphabet you're going to make a drug, a plastic, some sort of material, you're converting one functional group into another. Sadly, for this book, we will talk about the sort of the reactions of alkanes next semester or next session, because they put free radical halogenation reactions in the second semester, not the first. I can live with that. So what we've done is we've done alkanes, and now we're going to move to alkenes. So for the alkene functional groups, and we're gonna do these reactions. How do you make a double bond? We're going to get to that. But we always start when we do a new functional group with naming and a little bit about physical properties. Alkanes are still alkenes are still hydrocarbons, right? They're still made up of carbon and hydrogen. The only difference with an alkene is what's the hybridization of that carbon. It's sp2. And that makes the VSEPR geometry around this carbon trigonal planar. So it's trigonal planar. So for the alkenes then, all 4 of these, or all 6 of these atoms, the things that are attached to the carbons and the 2 carbons themselves, are all in a plane. An alkene is a planar structure. And there are alkenes are easier to react than alkanes. We'll come back to that. But for naming alkenes then, since it's an alkene, the ene is the suffix for the parent chain. So if you had, for instance, that alkene, we're still going to locate the longest continuous carbon chain in the molecule, but now our rules say that you have to locate the longest continuous carbon chain that contains the carbon-carbon double bond. So we still have, number 1, the longest carbon chain, but I'm going to add an addendum to that saying that includes the carbon-carbon double bond. So in this case, what's the longest chain? 1, 2, 3, 4, 5, 6. So this is now going to be a hexene. If it was hexane, there would be no double bond, and now it's an hexene that tells us, hey, you've got a double bond. So the parent name becomes the longest chain plus ene. Great. So if I said, hey, I have this hexene, draw its structure. What do I need to tell you? Where's the double bond at? Where the double bond is? What 2 carbons is the double bond between? Well, actually all I need to do is tell you what the first carbon's number is. So in this case, what would this be? Well, so the rule is going to be I have to number from the end closest to the double bond. So in this case, it's 1 hexene. Because if I don't say you have to number closest to the end of the first double bond, or first carbon of the double bond, then people are going to have different numbers. So this is 1 hexene. Okay, so longest continuous carbon chain that has a double bond, number from the end closest to the double bond. And that's what that number means. And then if I had substituents on here, I would add in the number and the name of the substituent. So notice that the numbering of the chain, the most important thing there is that it gets the lowest number for the alkene. Now if there was a tie, and you could go from one end to the other end and still have the same alkene, then we default to now number from the end closest to the first substituent. And we would be back to our rules from last week. So the naming of alkenes is pretty straightforward. Now I just have this issue of where to put the double bond.
So if you have a double bond between two and
Yes. So then it would be 2-hexene. If I had the double bond, in this case there's 1, 2, 3, 4, 5, 6. If I had it between, let's say I had the double bond here, then it's 1, 2, 3, 4, 5, 6, 1, 2, 3, and then 1, 2, 3. It wouldn't matter from which end I numbered. Just the lowest one from either of these ends, but let's say I put a methyl group there. So I'd have to go from the left, because going from here it's 1, 2, 3, 1, 2, 3, they're tied. But now I have to go from the end closest to the first constituent. So this would be a 2-methyl, or sorry, 1, 2, 3, it would be a 2-methyl 3-hexene. And that's not even correct. I'm missing something. So this would be 2-methyl 3-hexene. So, one of the bigger things with alkenes is that now we can have 2 different stereoisomers potentially for an alkene. So for instance, let's take the one I just drew. I could draw another 2-methyl I could draw another 2-methyl 3-hexene. But what's different about those 2 molecules? Just from looking at them. I moved it up, so now I've got different shapes. So these 2 molecules are stereoisomers, because in one case the chain is zigzagged, and in the other case the chain goes up. So those 2 molecules would have 2 different shapes. And so for double bonds, we could have 2 different 3-dimensional stereoisomers. So double bonds now have stereoisomers. Cyclohexane rings had cis-trans stereoisomers depending on whether the 2 groups were both on the same side of the ring or on opposite sides of the ring. In this case, double bonds are going to have cis-trans isomers depending on whether the 2 groups are on the same side of the double bond or if they're on opposite sides of the double bond. At least the simple ones will. So that's going to be a new stereoisomer that has, and that term is going to have to go into this name. So when you have a double bond, and one double bond, and one carbon in the double bond has 1 hydrogen and 1 hydrogen only, and the other carbon in the double bond has 1 hydrogen and 1 hydrogen only, we have 2 possible stereoisomers. We have cis and we have trans. Cis meaning same, trans meaning opposite. So those terms can only be used if one carbon has a hydrogen and if the other carbon has a hydrogen. And so we've got a hydrogen and a non-hydrogen group, a hydrogen and a non-hydrogen group. And obviously hydrogen, non-hydrogen, hydrogen, non-hydrogen group. So if I say I have the cis isomer, it doesn't matter whether you say, well, is it the hydrogen or is it the non-hydrogen groups? You say, it doesn't matter. Cis means either the two hydrogen groups are on the same side of the double bond, or the two non-hydrogen groups are on the same side of the double bond. There's no confusion. And trans would mean exactly the exact opposite. It doesn't matter whether I'm talking about the hydrogen or non-hydrogens, we get to the same answer. So you can use cis and trans in these two particular circumstances. Now, if you had the same group, attached to a carbon in the double bond, if you have the same group, there is no stereoisomer. There is no cis-trans. Because cis-trans means I have two different shapes. That means that if I switched two of these groups attached to one carbon, I'm going to get a different shape. Well, if they're the same group, if these two groups are the same, and I switch them, what happens to the shape? Nothing. They're the same. So you have to look and see if they're the same group if they have the same group on the same carbon, there's no stereoids. So cis and trans represent the stereoisomers when each of the carbon in the double bond has one hydrogen. So anybody psychic to figure out what the next issue is going to be? What? What if I have like a methyl group here, I've got like an ethyl group here, I've got a methyl group there, and I've got a hydrogen there? What if I've got three non-hydrogen groups attached to the double bond? And it's not too early for me to point out that the double bond has a maximum of 4 things. So if 3 of those are non-hydrogen groups, what do I do? We have to use another numbering scheme. Now, sometimes people will want to look at this and they'll want to say, oh, well, that's cis. And I'll say, well, it's cis if you do what? Well, if you're counting the methyl groups, right? If you're saying, well, the methyl groups are cis, which you can perfectly say. You could say that this methyl group and this ethyl group are trans, but to name this cis would mean that we all have to be in agreement that we're going to look at the same group. And then the issue would be, what if I got 3 different groups and 2 of them aren't the same? I can't even assume that the 2 same groups would be cis or trans. So now we have to have a different numbering scheme or a different naming scheme. So again, the IUPAC people, they're like, how do we come up with a scheme that every person will name it the same if they follow our rules? And so their solution was to develop, actually, I'm not sure if they developed or if they just used the existing Conn-Ingle pre-log sequence rules. Those were the rules that we used think it was just yesterday, or the day before, or it was on Tuesday, right? Coningo pre-log sequence rules were the ones that let us go number 1, number 2, number 3, and number 4 for priority groups. Now, we could have done those first and applied them to alkenes. And then when we got to the chiral centers, we would have just gone, oh, remember those rules? So hopefully if we have those under control, I'm going to assign priorities. And it's even easier than it is for chiral centers. Because what they did was they said, let's use the Coningo pre-log sequence rules to make like a new cis-trans system. So let's compare these two groups, and if I compare those two groups, which one has the higher priority according to the Coningo pre-log rules? Ethel? So again, I'm going to look at this carbon and say, carbon versus carbon tied, 3 hydrogens versus 2 hydrogens of a carbon, ethyl group wins. Now I'm going to come over here and I'm just going to compare those two groups of methyl versus hydrogen and which one has the higher priority. Methyl. And so now what I'm going to say is, okay, which are those two groups on the same side of the ring, or are they on opposite sides of the ring, just like cis or trans? But now I can't use cis or trans. I've got to develop a new nomenclature system. So what they decided to do was to go and use German. You might say, why? Well, because organic chemistry, for the most part, is a German science. It wasn't until the late 1800s, maybe the 1900s, well, I should probably say it was a European science, right? Because we talked about Pasteur. And I should probably even say it was a European science / Russian science, but at the time nobody really knew what was going on in Russia. Right? Because you had Stalin and dead people and all sorts of the Russian issues. But we haven't come to people like Markovnikov and Zaitsev. They're prominent Russian chemists who developed a lot of key principles in organic chemistry, or at least we're given credit for it. So basically organic was a European science, primarily German. The prominent American scientists, American organic chemists weren't trained in the U.S. initially. They were trained in Europe. And then we got the benefit of, all the Germans getting out of Germany during the wars. So what they decided to do is they decided to use German terms. And I took one semester of German 30 years ago, because when I was going to go to graduate school and was contemplating organic chemistry, the first thing you had to do was know German. And they actually had a German competency test you had to take. Fortunately, when I got to graduate school, they had eliminated that in favor of dictionaries. So I didn't have to take the German test. But I do remember I think these are S's actually. Enthagen and zusammen. I don't remember Enthagen, but it means across. And zusammen I do remember meaning together. Because one of the passages was two people that were zusammen wollen, which means they were living together. And I thought, that's kind of scandalous for a German, college textbook. This is, another day and time. But so zusammen means together, and Enthagen means across, which gives you then the EZ method of determining stereochemistry for alkenes. So Enthagen is the equivalent of trans. Zusammen is the equivalent of cis. How do you remember that? Z, Zame, Zide. It's a mnemonic. Probably not a good one, but it works. So That's your cis and your trans. So then you go to this molecule, you say, oh, okay, our two high priority groups are across from each other, so this is the E isomer. And the E comes usually at the beginning of the name. So in this case, prior to doing this, I would have said, here's my 5 carbons in the longest chain. I would number from the end closest to the first substituent. So I would start with the methyl group up here. And so in this case, I would have an E, 3 methyl. And ethyl is E, 3 methyl, 2 pentene. And actually, so there's an old IUPAC system and a new IUPAC system for where the number goes relative to the ENE. So I would accept E3-methyl-2-pentene. The IUPAC purists would call this E3-methyl-pent-2-ene. Because I just remembered in the new system, they put the number right before the suffix. So it's a pent-2-ene, as opposed to a 2-pentene. It doesn't matter for this. It may matter for top hat. Yeah. Because I've got the longest chain, right? So I've got 1, 2, 3, 4, 5 in the longest chain. So in this case, I don't have 6 carbons. This was a different molecule than the one before. We could go back and name that now cis or trans. But that's the name of this one. So this would either be E3-methyl-2-pentene or E3-methyl-1 or E3-methyl-pent-2-ene. I'll take either one. But the critical part here is it's E. So cis or trans is still allowed to be used, but it can only be used if each group has a hydrogen. Each carbon has a hydrogen. Once you have 3, you can't use cis or trans anymore. Can you use E or Z instead of cis or trans? Yes. So you could go back to the molecule that we did here. You could go back and you could say, okay, one of these is E, one of these is Z, or one of these is cis, one of these are trans. So you can always use EZ as a substitute for cis or trans. But you cannot use cis or trans as a substitute for EZ. So the cis and trans, so for the cis and trans, it has to look like this. It has to look like that. 1 hydrogen attached. Each carbon in the double bond has to have 1 hydrogen and something else. 1 hydrogen and something else. So that when I'm looking at that, if I said, hey, I have the cis, then it doesn't matter whether you're saying, oh, the 2 hydrogens are cis, oh, the 2 non-hydrogen groups are cis, I get the same answer. So for cis and trans, you've got to have that 1 hydrogen attached to each of the carbon. But once you have 3 non-hydrogen groups attached, we got to go to the EZ system.
So, basically, if you have 2 to use sister train, you can only have two groups.
You can only have two non-hydrogen groups coming off the molecule, and they have to come off the two, one each, so that it looks like it has to look like these, because that's the only way that it's understood that the two groups are either cis or trans. If the other two are hydrogen. Oh yeah, no, these two groups don't have to be the same. Because again, it doesn't matter what we're referring to. I mean, technically we're referring to the hydrogens. But it doesn't matter because it's understood. But E or Z is very technical in terms of that. If these were E or Z, hydrogen always has the lowest priority, so those other two groups all automatically have the highest priority. So that's what we kind of skipped over with the double bonds. Was first of all the naming. And the naming is back in chapter 2. Because in this book they name everything in chapter 2. We're going to break that up. And then they introduced the Coningle pre-log sequence rules with alkenes, and I decided to do it with stereochemistry, but it doesn't matter. That makes this pretty straightforward, I guess. You just have to remember to put the cis or trans or E or Z in there. So there's a molecule. What we can do is take our 5-minute break or so, and then when you come back, name that. I'll go to my office and I'll grab my iPad that has everybody's name on the roulette wheel of death, so that then I can push the button and it'll come back, and and I can call on somebody without picking on them. At the end of class. Then I'll talk about them. Yes. Today I will. Yes, today. Yeah, I just have to scan in the answer key and put it online. I haven't done that. Do we have a name? Somebody give me a name. Aria? Hold on. 4 bromo, 8 chloro, 2 ethyl, 5 methyl, non-4-ene. You want to change it? Okay. What do you got? Okay.
5, 8, 1,
Uh-oh. Okay.
6.
Decene. Okay. Six decene. So 6 bromo, 2 chloro, 5,8 dimethyl, 6 decene. Anybody have another name? Yeah. Okay, so we got a 5 decene.
Oh, that's what I
Yes. So you're accepting his friendly amendment that, okay. I don't know.
I'm pretty sure either way, double one plus 5. If you look on the left,
So do you want to keep the bromo as 4 or 6 or? So then we got to put an E or Z in there. That's true. What is it? Z? So there should be a Z in front of both of these? Okay. Any other names? Do we want to vote? You can ask any question you want. It's a good question.
you expect me to take the CH2s.
So we have a 10 carbon chain. Yes. We have to, we're going to do the same thing. We're going to compare these two groups, and to determine high priority, we're going to determine these two groups and determine high priority, and then they're either both on the same side or both on opposite sides. So are we withdrawing the first name? Does everybody? Okay. So what was the longest chain? 10. What do you want to start with? What do you want to start with? You want to start with this carbon? Without numbering, let's just determine the longest chain. So let's start with this one, and where should I end up? Here or here? Here or here? Top. All right, so let's take that. So longest chain is 10 carbons. Longest chain that includes the double bond. So why did I do that? And so the reason I added the CH2, CH3 on top was just to reinforce that's always our first step. So there's the longest chain with the carbon double bond, and we've got a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 carbons. So if you just went to the methyl group with 9 carbons, again, double check all your chains. So we got 10 carbons. So should we number left to right or right to left? Left to right? Or right to left? I got a number from the end closest to the first substituent or the double bond? Double bond takes priority. So if I number from right to left, it's 1, 2, 3, 4, and 5. If I number from the left, it's 1, 2, 3, 4, and 5. Tie. Okay, so what's going to break the tie? The first substituent. So numbering from the right, 1, 2, 3, and that 3 group is a methyl. 1, numbering from the left-hand side, 1 and 2. Don't even have to alphabetize. Chlorine number 2, methyl number 3. So it's going to be number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, 9, and 10. So when the question was asked about should the bromine be number 5, it would be if we number from the right hand side, but the priorities are, again, longest chain with the double bond, number from the end closest to the double bond, that was tied, number from the end closest to the first substituent, a 2 versus a 3. If it would have been a 2 versus 2 or 3 versus 3, then I would have used alphabetization, but I didn't need to. Okay, so then that gives us what? I erased it. A 6 bromo and a 2 chloro, then a 5,8 dimethyl, 5 decene or dec 5ene, either one. And then you always have to go back and remember the double bond. Now, is it cis or trans? No. It's got to be E or Z. So now as I'm looking at this from the E or Z standpoint, for the left-hand carbon, I'm comparing this carbon and the entire rest of the group versus this carbon and the entire rest of the CH3. So which group is the higher priority? The top, because it's attached, because this is a carbon versus carbon, 3 H's versus 2 H's and a C. Right, that's what this has, 2 H's and a C. This carbon has 3 H's. So top one wins priority. Over here, what do I got? Bromine versus carbon. Who wins? Bromine. My 2 high priority groups are on the same side, and so that makes it Z. And sometimes you can put the parentheses in or not. A lot of times you'll see the Z, you'll actually see the Z in italics. So it's C6 bromo 2 chloro 5,8 dimethyl 5 decene, or dec 5ene. So that's how we do it. So again, just for, Monday, could I ask you to just do an E or Z, just say is the double bond E or Z? Yes. Could I give you a molecule to name a number and it might need an E or Z? Yes. Or a cis or trans.
What is that double bond that would also double bond the solution that's not?
Then, yep. So in other words, if I had something like this, I have a double bond here and then over here. Let's say I made that CH3 group another double bond, and then let's just keep it there. How would you name this molecule? And I'll leave all the other extracurricular stuff out. we would then need to find the longest chain that contained the double bond. So, and actually we would need to find the longest continuous chain that contained both double bonds. So this one would be what? A 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be a 9 carbon chain. Number from the end closest to the first double bond. Well, in this case, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, and 9, because the double bond's at the beginning. The rule is it's got to be the longest chain that contains all the double bonds. Now, so I can't go up to the ethyl group because I have to have all the double bonds in the longest chain. So now what do I have at carbon 2? I've got an ethyl. So this is a 2-ethyl. And now, how do we indicate that the molecule has 2 double bonds in it? It would be a 1, 4 non. Well, so now I have to tell you in the ene that it's got 2 double bonds. So it would be a diene. Except non-diene doesn't sound, well, I guess it could be non-diene or it could be non-diene. You just add the A for pronunciation. So it would be 1,4 non-diene. Or, and this is why I think the IUPAC rules were revised, was that it would be non-1,4 diene. So that you didn't have to worry about putting the A in place. So if you have multiple double bonds, you have to have multiple numbers, and then you have to say diene or triene in the parent name. Probably not, but it's fine whether there's a space, a dash. I'm sure that, actually I think the L and the N would be next to each other, but I'm not as strict as the IUPAC people on spacing. Numbers maybe, groups definitely. Yes, we do. That's what's missing from this structure is either easy or cis or trans. I don't know, that's the question. That is a question. Do we have to indicate the stereochemistry of both double bonds? Easy enough to ask the question. What's the stereochemistry of the 4,5 double bond? E or can I use trans for the 4,5 double bond? Yes? No? No? Yes? So this carbon has what attached to it? Number 5. It's got a non-hydrogen group and a hydrogen group. What's 4 have? A hydrogen group and a non-hydrogen group. So I could use cis or trans for the 4,5 double bond. So you can either say cis trans, or you could call it, you can either call it trans or E, your choice. And when I say your choice, I sort of mean your choice. Like, you could say, well, you know, can I just forget about cis or trans? No, because I'm going to use cis or trans where appropriate. So you have to know what those terms mean. But if you wanted to say trans or E, both would be acceptable. So the 4-5 double bond is E, or trans. Now what about the 1-2 double bond? What's it? What were you going to say? No. So carbon number 1 has the same group attached to it, same 2 groups attached to it. So it's not my personal choice not to call it anything. It isn't either one. In other words, the reason that we have to call it cis or trans is because if I replace 2 groups, I would get a different 3-dimensional structure. If I replace this hydrogen with this hydrogen, what do I get? The same 3-dimensional structure. So when the groups are the same, you can switch them without changing the 3-dimensional structure. If they're different and you switch them and you get a different 3-dimensional structure, that's why we have to have the cis and the trans to tell us which 3-dimensional structure we have. So there is no stereochemistry there is no cis or trans, there's no cis or trans, or E or Z for carbon, the 1-2 double bond. So I only have to define the carbon 4-5 bond. Actually, no, not in this case, but we will. So if we had multiple bonds with multiple EZ designations, what would happen is, what did we say this one was? E? Now, if I just said E, I would be okay because number 1 doesn't have a cis, trans, or EZ. But just for the sake of clarity, since we're new at this, I would say it's the 4E, that it's 4E2 ethyl non-1,4 diene. That tells me that the double bond starting at carbon 4 is the E stereochemistry. You could also say 4 trans. Now, if number 1 had a cis, trans, or EZ stereochemistry, then what we would have is then we would have a 1 E or Z, 4 E stereochemistry.
How come you couldn't put the E or the Z and identify
Because that's not what the rules are. The rules say it has to come at the beginning. And it's, well, do I want to go down this road? No, what the hell. So you might say, well, how did they develop these naming rules? Like, why are they developed the way they were? These naming rules were developed before computers. And you might say, so what? Well, I mean, when I was an undergraduate in the early to mid 80s, we had computers. We had computers that had a green screen and that's it. There were no colors yet. But there was no internet. And so if you wanted to know physical properties about a molecule, you had to go to the library and look in these books. So the naming system had to be conducive to alphabetical naming in books. So that if I wanted to know about this, I number one would have gone to the non section, the ends, and I would have looked up either nonadiene 1-4, or it would have been 1-4 nonadiene. So I would have had to go through the ethines. Wouldn't have gotten to the propenes yet because that's not alphabetical. So I would have gotten to the N, found 1,4 nonadiene, comma, 2-ethyl. And 2-ethyl would have come before methyl, propyl. A bromo would have come first. So the numbering scheme, they took the parent name and number, and then there would have been a comma, and then there would have been the prefix, whatever came before that. So this was their method of organizing it into books by alphabetization. Even with computers, that's sort of the way we do it now. What was the point of looking it up? You haven't had to look up any physical properties of your molecules in lab? Or how to synthesize it? Or what research has been done on it? So and all of this is Dr. Google has taken care of a lot of this stuff, right? Because we can just search on Google and its cousin Wikipedia, which has all sorts of fine unverified information. And whatever else you find, Sigma Aldrich is now on the computer. But back in the day, if you wanted to know anything about a molecule, you didn't have the internet to search, so you had to go to these books. One of them was called the Chemical Abstracts. And so if you wanted to know, for instance, the physical properties or how to synthesize this molecule, or what was known about the molecule, you would have to go to the Chemical Abstracts, find it, and then it would give you the references. It would give you references on that molecule. And so then you could look up the references in the individual journals, which were on paper as well. So the Chemical Abstracts had the compendium of all the molecules that had been made to that point, including a unique number that now you can search on the computer and immediately find out all the information on that molecule. So we had a senior seminar course where we had to give a couple talks, but then we had to do a paper on the molecules, so we had to search. So that was the entree into the literature. Nowadays, we still have Chemical Abstracts. But what we do is we type in the name, we find the number, and then then it'll tell us all the papers that have been published with that compound. And then we have to search them one by one to see if it is relevant to us. So that's where the alphabetization scheme came from. Was it had to fit into a book, and there had to be a logical order to it, and it was all alphabetical. So non-ane would have come before non-ene. Nonadiene might have come. It might have been before the enes or after the enes. I'm not quite sure. And this is why we don't alphabetize the dyes and stuff. So that was where all the numbers came from. That's the equivalent of I walked to school uphill both ways, 10 feet of snow. But well, technically dinosaurs and humans didn't exist at the same time, right? That's a topic for another class. Yeah, no, I know, but somebody will go online, they'll find the video, and then they'll protest me. But that's what we had to do. So nowadays, in the Sigma Aldrich book, did Dr. Simmons take those of you in lab to the computer room and show you where the books were? No, probably not yet. But there is in the Carabine computer room, there is a Sigma Aldrich book. And the Sigma Aldrich book has the physical properties of all the chemicals you can buy from them. So what Sigma and Aldrich did was they decided they would make their catalog would have useful information in it so that you would keep that on your desk. And so when you needed the physical properties, you'd be able to find them. But more importantly, when I need to order a chemical, oh, there's the catalog right there. I know which one to order. So it was marketing as much as it was chemical information. But I don't think they were the first chemical company to do that, because they didn't exist until the 40s or 50s. I think there was another one in the 30s that had a little tinier book that had all their products in it as a reference book. I think I have a copy of that one. But so somebody else started it before the 30s. I always thought that was brilliant marketing. But nowadays nobody looks at paper. Everybody looks online. All right, so naming. And obviously there's the naming problems that are going to be in the Top Hat textbook. But I can ask you to do a name or easy, or both. Probably not. Probably name. Again, drawing the structure from the name gives you a double check that you got the right name. Well, I would in the same way, like if I asked you to do a chair cyclohexane again or a Newman projection, right? So you got to know the names, and you still have to know your functional. You still have to know your common names. You still have to know isopropyl, sec-butyl, etc. You still need to know those for Monday. Okay. So, next thing that we are going to I'm going to introduce you to are some basic fundamental definitions here for our next series of topics that we're going to get into detail on next week. Which is, I didn't say that. Remember yesterday I said once I do that everybody doesn't pay attention. So that's the last thing I'm going to say. But these are the basic terms. So and this is following in chapter 7 now, where they're going to define the basic terms. They foreshadowed all of this in chapter 3, but when I did chapter 3 in the fall, when I did it in the order number 1, number 2, and number 3, by the time we got to chapter 7, most people had forgotten about number 3, so I just skipped right this time to 7. So here's some of the basic definitions that we need to know. Electrophiles and nucleophiles. A substitution reaction versus an elimination reaction. And then we're also going to talk about unimolecular versus bimolecular, but I'll build up into that. So, electrophiles and nucleophiles are going to be, an electrophile is going to be an electron-poor species, and a nucleophile is going to be an electron-rich species. So what would be an example of each? Well, for the nucleophile, let's say I had hydroxide ion. And I said that hydroxide ion is going to be electron rich. What's making it electron rich? What about the oxygen? The lone pairs, the fact that it has what kind of charge? A negative charge. Now, I anticipated somebody say the negative charge, and then I would say, well, where does that come from? The electron pairs. So whether you say the negative charge or the electron pairs, that's what makes the molecule rich. Now in the chemistry world, you can compare this to other worlds. That's for another class. But in the chemistry world, those that are rich want to get rid of their richness. Right? The ideal molecule in the chemistry world has what kind of charge on it? 0. So in chemistry, when you have a negative charge, what do you want to do with that negative charge? You want to get rid of it. You want to share it with a species. What kind of species? A positive one that's electron poor. So what would be an example of a positive species that OH minus would give its electrons to? H plus. So H plus is an electron poor species. It's an example of an electrophile. And the hydroxide is an example of a nucleophile. So in the chemistry world, what happens with hydroxide and H plus? The hydroxide takes its lone pair and it donates it. Actually, it doesn't donate it. It shares it with the H plus, and now we made water. Now we could go back to general chemistry and we could also talk about this reaction of hydroxide plus H plus as what kind of reaction? Acid-base, specifically what kind of acid-base reaction? No, you're right, a Lewis acid-base, or starts with B, or a Bronsted-Lowry acid-base. Now the one that's most appropriate to organic is actually the Lewis acid-base. So what we then have to remember is, well, what's a Lewis acid? The Lewis acid is the one that has extra lone pairs that it can donate, or lone pairs that it can donate. Nope, sorry. Right? It's a Lewis base. And the Lewis acid is the one that has the ability to accept the electrons. So what's opposite about Lewis acid's base and Bronsted-Lowry acids and base? Well, in Bronsted theory, the acid is the one that donates the proton, and in Lewis acid, the acid is the one that accepts the electrons. And that's the one that's more appropriate because the species that's accepting the electrons is the electrophile. The species that's donating the electrons, the Lewis base, becomes the nucleophile. And so if you take your Latin or Greek or whatever language that is, phile means like or loving. So an electrophile is a negative loving species, and a nucleophile is a positive loving species. So why they did this is a historical thing in organic. Why they just didn't say, you know what, let's just use the Lewis acid-based terms so that they'll become more relevant in general chemistry, but then, you know, we don't have to change terminologies. They didn't do that. They came up with their own names. So we're going to talk about electrophiles and nucleophiles. So electrophiles with the positive species and nucleophiles with the negative species. And in the chemistry world, the nucleophiles always have to donate to the electrophiles. And when we get to a point where we have different electrophiles that have different positive charges, the nucleophile, the electron rich, always have to give to the most electron poor. And electron rich species cannot share with each other. So, chemistry world is a lot different than the world in terms of rich, poor, and sharing. These are the rules. Now, what we want to talk about is we're going to talk about a carbon with a positive charge. We'll get to that. But we also can talk about an electrophile being something like this. Because we learned last week that what would be the charges on the carbon and what would be the charge on the chlorine. What kind of negative? A delta negative, a partial negative. And what on the carbon? Partial positive. So when we have a halogen attached to a carbon, we've now created that carbon as an electron rich, electron poor. That carbon is now electron poor, right? Because it's got a delta positive charge. Is it electron poor as if it was a full-blown positive one charge? No, but it's still poor. Who made it poor? Chlorine, by taking some of its electrons away from it. But they're still sharing. Yeah, they're unequally sharing. So that electrophile could react with our hydroxide that's electron rich. And so what will happen in some cases is that we will have a nucleophile with a negative charge, and it will come in and it will want to share its electrons with that electron poor carbon. But that carbon has a problem. It already has 4 bonds, so if it's going to now accept the electrons from the hydroxide, it's got to do what? It's got to break a bond. So somebody's got to leave. So who's going to leave? No. The chlorine. You could say, well, why not the hydrogens? Because the carbon is actually sharing its electrons with the hydrogens tighter, because the electronegativity difference isn't as much. That's a more pure sharing than it is with the chlorine. The chlorine's already got unequally a bunch. So if the hydroxide comes in and shares its pair of electrons with the carbon, the chlorine's going to, you can write all the people scenarios for this that you want. Just don't bring them to class. But the hydroxide's going to come in and the chlorine's going to leave. So now the hydroxide's going to be attached to the carbon, And the chlorine is now left with a full-blown octet, which means it has the negative charge. And so in this reaction, what I've done is I've reacted a nucleophile with an electrophilic carbon, meaning that it's electron poor. And I've also created then a nucleophile on the other side. So I've substituted one nucleophile for another. And that was the key word. I've done a substitution reaction. I've replaced the chlorine with hydroxide. So this is what's called a nucleophilic. This is a nucleophilic substitution reaction. Because I'm substituting one nucleophile for another. Yep. Right, so the carbon's like, well, okay, I'll give you the carbon, I'll give you the electron chlorine, because now the oxygen's going to share a new one with me. So on the carbon, there's no net change. And even in the end, the oxygen is still partially sharing more of or owning more of the electron density than the carbon is. So the carbon just basically had one group substitute for another, and now you could say, well, the carbon owns a little bit more electron density because the oxygen isn't as electronegative. But the point here is that we're going to use nucleophiles and electrophiles to describe a substitution reaction where I'm substituting one nucleophile for another. That's going to be called an SN reaction, substitution nucleophilic. This reaction is also going to be it's going to be a substitution reaction. When we get into the details on this, we're going to have to talk about explicitly step by step how this process occurs. And there's going to be an SN1 and an SN2. But they're going to be based on the idea that the carbon's electrophilic, the water, or the hydroxide in this case, is nucleophilic, and this chlorine that left is going to be called the leaving group. So the nucleophile is going to come in, and it's going to, I will use the term over and over again, it'll kick off the leaving group. Is there anything stopping the leaving group from coming in and attacking the carbon, coming in and sharing its electron? Attack is such an aggressive word. It's going to share its electron with carbon and kick the hydroxide group out. Yeah, there's something stopping it, and that is that chlorine's a better leaving group than hydroxide is. So these leaving groups have rankings. The nucleophiles have rankings. So we're going to have to talk about what the rankings are. We're going to have to talk about how solvent affects this. We're going to have to talk about the nitty-gritty details of how this reaction occurs. And we're going to have to talk about the kinetics of this reaction, because that's where the one and the two come from. Okay.
Just looking at this, is it more so that the chlorine can't come back because of the old bond connected to the carbon? That's a stronger bond than hydrogen bond?
It's a little bit stronger bond from the standpoint of the CO being a little bit more equal in sharing. But actually, what we're gonna find is that the leaving group ability is based on one thing, and that's its basicity. And hydroxide is a much stronger base than chloride. In general chemistry, we don't even consider chloride to be a base, but we consider hydroxide to be a strong base. So strong bases make lousy leaving groups, and poor bases make great leaving groups. And so early on in chapter 7, that's what we have to lay out, is the strengths of these nucleophiles and the strengths of these leaving groups. And so that's what we'll do on Monday after the exam. Is I'll continue this and we'll get down to some of the details on substitution reactions. And then we'll spend next week talking about those and their counterparts, which are the elimination reactions. And we'll have our first introduction to mechanisms. Okay. So I will send out, and I could have sworn last week I sent out an email on Thursday that had a listing of the topics, but then on Saturday I tried to find it and I couldn't, so I will do that this afternoon. Exam. So I will scan in the exam answer key, which I didn't get a chance to do yesterday, and I will post it in, actually I'll send it to you and then I'll post it in Monday's folder. Next Monday's exam will also include two problems from this exam, not the exact problems from this exam, but two additional problems. And the two additional problems will be, I'm going to ask you to do another chair cyclohexane, draw the four structures, 2 cis, 2 trans, and rank them, number 1 to number 4. Look through your exam. If you had an issue, it was usually one of 3 things. You have to make sure you can put the axial and equatorial positions in the right directions on the carbons. And then you have to get the right alkyl group that I give you. And that was usually the big downfalls. Because if you don't get the axial and equatorial positions in the right place, it's like I don't know what you're talking about. Now I've done thousands of these, so I kind of know what it means when you put it in the wrong direction, but yet you assume this one's above the plane or below the plane. But you want to make those bonds look exactly like they did when we first drew them out. And then if I say a tertiary group or an isopropyl group, you want to make sure it's an isopropyl group. Then the Newman projections, I will give you another Newman projection with a name, and you'll have to write down, looking down the C3, C4 bond or whatever bond, you got to make sure that you have the front carbons groups correct and the back carbons groups correct. We did 3 methyl pentane. That meant that the front or the back carbon, depending on how you looked at it, had to have a methyl and an ethyl, and the other one had to have a methyl. So if you had like 5 carbons, or 5 of the bonds, 5 of the 6 bonds had carbons on it, I couldn't answer it. I couldn't rate that, because that's like your own problem. So you have to make sure you write the molecule that I gave you. So I'm going to have those on the next exam. Will they count for the next exam? Yes. And I'll add an incentive to it that if you do better on that, if you do better on those problems than you did on these ones, which, I should have scanned these in. Whatever you get on the next ones, I'll add on to your score here. And if you go above 100%, that's fine. Okay. So the next problems I'll use in adding on to this one. So if you're a little freaked out and that's what you missed, make sure you get those under control for Monday. This is new. I usually don't do this. I have other faculty colleagues that will do this, but my goal is that we really want to make sure we can do this with Newmans and with. So like I said, if that's what you missed, you have the opportunity to make that up on Monday's exam. So it's a second chance. But I wouldn't count on a third chance. All right, so make sure you can do that, and I'll put that in the, let's see, I recorded it.